All right, everyone, our homework last night was page 410, number 1 to 10. Any issues with those questions? Please, on page 410. Yep, number 10. Any others? 9 and 10? Any others? Going once? Going twice? 9 and 10 it is then. All right. Number 9 says, two tuning forks are generating sound waves with a frequency of 384 hertz. The waves from one tuning fork are generated in air where the speed is 350. The other one is generated in water where the speed is 1500. So clearly the speed in water is much, much faster than the speed in air. Does anybody know why? Why is the speed of sound in water a longitudinal wave, right? Why is the speed in water much greater than the speed in air? Jazzy? Right, particles are closer together. Longitudinal waves transfer by collisions of particles, right? By collisions of particles. If you've got these particles that are a lot closer together, like you do in water than you do in air, then the collisions are going to take place much, much easier, and it's going to travel faster, dramatically faster here. We want to find the wavelength for sound in air and in water, and will we hear the same musical note underwater as we did in air? Okay, let's look at question A here. We want to find the wavelength, so we're going to say V is equal to F times lambda. We get two equations here that we could use, right? V equals D over T, V is equal to F times lambda. This is the one that's going to get us wavelength. Lambda is equal to V over F. V is 350 meters per second. The frequency is 384 hertz. What's that work out to be? Somewhere around, I don't know, 0.9-ish? What do we get for that? 0.911 meters. All right, good. What's the wavelength in water? Well, we're going to use the exact same method, except, of course, our speed is going to be a lot different. This time it's going to be 1,500 meters per second divided by 384. That's going to give me somewhere around, I don't know, 4-ish? 3.91? 3.91 meters. All right, so the wavelength clearly is dramatically longer in water than it is in air. Why is that the case? Well, because the medium causes a difference in speed. When you have a difference in speed, you have a difference in wavelength. Okay, if the speed is higher, the wavelength will be higher as well. All right, would we hear, question C, would we hear the same musical note underwater as we did in air? Who says yes? Who says no? Okay, somebody that said no, give me a reason. Yep. Okay, wait a second though. It muffles the sound, so you're saying it's not going to be as loud, or are you saying it's not going to be a different pitch? Okay, okay. Anybody else have something to add, or to change, or something completely different than what you just said? The pitch of the sound that we hear, the musical note is based on what? Speed, frequency, or wavelength? Frequency. Frequency. Yeah. A C note, I'm not even sure what a C note is in terms of frequency. Okay, music people might know that in terms of what it is in terms of hertz. But it's always the same, right? A C note is always the same number of hertz. Once a wave has been produced, the frequency never changes. So it doesn't matter whether that sound is produced underwater or whether it's produced in air. The frequency will be the same. Okay, if you've got air molecules vibrating back and forth at 300 hertz, it doesn't matter how fast they're moving. They're still going to be vibrating back and forth at 300 hertz in water as well. Therefore, the sound that you hear underwater would be the same sound that you would hear above ground in air. Does that make sense? Because it depends upon frequency. Once a wave has been made, the frequency doesn't change. The speed and the wavelength can, the frequency doesn't. Okay? And question number 10. This one says a radio speaker generates sound that your eardrum can detect. What does the operation of the speaker in your eardrum suggest about the nature of sound waves, and how does this nature of the medium, air, through which sound travels support your assumption? Look, the direction of oscillation, the direction of vibration of the radio speaker is back and forth this way, horizontally. The direction of vibration of your eardrum is back and forth horizontally. What does that tell you about the nature of the wave? the fact that these two things both vibrate back and forth horizontally. Which way is the wave traveling? Up, down, right, left? Wave travels from the speaker to your ear, right? Okay, from the speaker to your ear. It travels horizontally. The direction of oscillation is horizontal. Which type of wave has the particles vibrating in the same plane or parallel to the direction of motion of the wave? Transverse or longitudinal? Longitudinal. So what does it tell you about the nature of the wave? It's a longitudinal wave. Sound is a longitudinal wave. How does the nature of the medium through which the sound travels support your assumption? Well, what do we say about longitudinal waves? What do we say about transverse waves? Transverse waves can't be propagated in a gas. Air is a gas. So what kind do you have here? The diagram shows us that it's got to be a longitudinal wave, but the nature of the medium, the fact that it's air, also tells us that it's got to be a longitudinal wave as well, right? Can sound travel through steel? How many people have ever seen the movie Stand By Me? A couple people? 3 people? Okay. There's a scene in the movie where these boys, they go out, just these little kids, they go out and just playing along the train tracks or whatever, and they find a body, a dead body. And at one point, they're walking along the train tracks, and they want to go through this train tunnel. And what do they do to determine whether they can go through the train tunnel? They put their ear down to the track, okay, and listen for the train on the track. Why do they do that? Didn't work out, by the way. It seems to me, if I remember right, they ended up walking through the tunnel, and there was a train coming, wasn't there? Was there? There was a tunnel there too, wasn't there? Was there? Okay. Why would you put your ear down by that train track? Yep. Well, why can't you hear through the air? Yeah, I don't know about better, but faster, right? So listen, if sound travels at 350 meters per second through air, and it travels at, I don't know how fast it travels in steel, let's say 1,600 meters per second through steel, then it travels about 4 times or 5 times faster through steel than it does through air. Doesn't mean it's necessarily going to travel any better, but what it does mean is that you're going to hear it sooner when it's traveling 4 times as fast, right? If the sound is taking 4 seconds to get, it's taking 20 seconds to get through the air from the train to you, then it's only going to take about 4 or 5 seconds to go from the train through the steel to you. So you're going to hear it sooner, which means if you want to walk through a train tunnel, you want to hear the sound sooner because you're going to be able to hear it further away. Okay. Now, what does this have to do with this question? Steel is a solid. Is sound a transverse wave or a longitudinal wave as it travels through the steel? It's a longitudinal wave when it travels through air, right? Is it a longitudinal wave when it travels through steel? Sure. No, it's longitudinal. Sound is always a longitudinal wave. Okay. Now, if you have a wave moving through a gas, it needs to be longitudinal. You can't have a transverse wave traveling through air. But if it's traveling through a solid, all bets are off. You can have a longitudinal wave or a transverse wave. So the nature of the medium doesn't determine what kind of wave that we have. It just sometimes limits what kind of wave that we can have. If it's steel, it can be transverse or longitudinal. If it's air, it's got to be longitudinal. Okay. Yesterday, we spent some time looking at wave behavior at boundaries, and we found that there were 2 things that could happen when a wave struck a boundary from one material to another. One was reflection, one was transmission. And we looked at specifically at the reflected ray, reflected wave, what happened to it. We saw that 2 things could happen to it. One, it could be reflected right side up. One, that could be reflected upside down. Do you guys remember from yesterday when the wave was reflected right side up? Picture the demonstration that we did, okay? The wave went through the slinky, all the way to the other end, and encountered a boundary. The first boundary it encountered was somebody's hand. The second boundary that it encountered was the air. In which case did it reflect back on the same side as it went down on? Okay, when I sent the wave down from Slinky to air or from Slinky to Abby's hand. Which time did it come back on the same side? The air. So when we're going from a more dense medium to a less dense medium, Slinky to air, it's going to reflect back on the same side. In other words, when it's not attached, it's going to reflect back on the same side. When the end of the Slinky is attached, or when it's going from less dense to more dense, i.e. from Slinky to hand, it's going to reflect back on the opposite side, upside down. The law of reflection, we didn't see this yesterday because you can't really do this with a Slinky. Here's my boundary right there, the solid line. The dotted line is what we call the normal line. It's a line that's 90 degrees to the boundary. If we have a wave coming in like this with a certain angle that we'll call theta I, then that wave will reflect off at a certain angle this way that we call theta R. What do we know about the values of theta I and theta R? They're the same. Theta I equals theta R. The angle of incidence equals the angle of reflection. Okay, that's the law of reflection. Now, we ended off yesterday talking about transmission. When the wave goes from one medium to another, we always have some reflection and some transmission. Sometimes it's more of one than the other, okay, but there's always some of both. When it transmits, when it moves from one medium to another, what's going to change? What always changes when, say, water goes from deep water to shallow water, when light goes from air to glass, when sound goes from water to air, what always changes? The speed. The speed always changes. What else will always change? Goes along with speed. The wavelength, good. If speed goes up, the wavelength will go up. If speed goes down, the wavelength will go down. What sometimes changes as a result of the speed changing? This one, it depends upon how the wave ray strikes the boundary. What sometimes changes? The direction. Yeah, if it strikes it at an angle, then the direction will change as well. If it strikes it straight on, the direction will stay the same. What is going to stay the same for sure? What never changes? Talked about this as we were going through the quiz, right? Frequency, not through the quiz, but one of the problems that we just did. The frequency. Once a wave has been produced, the frequency doesn't change. Okay, it never changes. To go from one medium to the other, from air to water, might slow it down. Okay, it might speed it up, depending upon what wave it is. The wavelength will change as a result of that, but the frequency won't. The pitch of the sound or the frequency of the wave will always remain the same. Okay. We just got back from our field trip to West Ed on Friday, and that's the field trip that we always do. Once, however, we took part of a class to the water park for a field trip. The reason we did that is because they were doing it. They had this group of students had designed this special project for the water park, and we wanted to do that, so we let them do it. It took about 10 of them to the water park to do this special project. One of the things they had to do was to find the frequency. I forget whether they were finding the frequency or the wavelength or the speed of the waves in the wave pool. I can't remember which one it was. But the bottom line is, it didn't matter where they did it in the wave pool, shallow water or deep water, the frequency was no different. Now, if you look at shallow water versus deep water, you're going to find the speed and the wavelength are different. Okay? As water goes from a deep place to a shallow place, the speed changes. The wavelength changes. They get closer together. The waves get closer together. Speed slows down, wavelength gets smaller. But what doesn't change? Okay, if you measure the frequency is going to be the same in the shallow water as it is the deep water, because once it was produced, it never changes. Right? Let's shift gears a little bit here. Let's talk about another phenomenon called interference now, interference of waves. All right, you just saw the demonstration. When two crests hit each other on the Slinky wave, what do we find? We got a bigger crest, right? When two troughs hit each other, we got a bigger trough. When a crest hit a trough, we got a smaller crest or trough. They canceled each other out effectively, which produced what we call destructive interference. Two crests, two troughs, constructive, a crest and a trough, we get destructive. What I want to do here right now is analyze exactly what a particular wave will look like as it passes through another particular wave. I'm going to give you a handout that shows exactly what we see right here so you're able to draw the same thing as I am. We have two waves up on the board here right now. One of them is bigger than the other. What does the resulting waveform look like at this moment? One half of a second after these waves have passed by each other, the wave will look completely different. But what does it look like at the moment that those two waves are in exactly those two positions? We're going to use something called the superposition principle to figure out what that wave is going to look like. The superposition principle simply involves adding numbers and then drawing dots and then connecting those dots. Doesn't sound very hard, and it shouldn't be very hard. What I want to do is look at where these two waves overlap. That's my important section. Now, I want to count up how big both of those waves are, or measure how big both of those waves are at as many points as I can in that interval. Okay, I've got it drawn on graph paper here, and the reason I've got it drawn on graph paper is because it defines well for me where I should draw, or where I should count and draw my little dots. Okay, on the first vertical line that we've got drawn past this blue line here, in other words, this vertical line, we'll call vertical line number 1, number 2, 3, 4, 5, 6, 7, and 8. On the first vertical line, the first wave, wave number 1, is one block above the equilibrium position, the horizontal axis. The second wave, sorry, the first one I should say, is 2 above. The second wave is 1 above. 2 plus 1 is equal to, I hope you know this. So what does that wave look like at that point? If this was two slinky waves, okay, Tom sent a slinky wave from one side, I sent a slinky wave from the other side, what's it going to look like at that exact point? Well, it's going to be up here. The slinky will be at that point where I have the X labeled. Okay, next one we've got 2 above and 2 above. 2 plus 2 is 4. So the waveform is going to be right there. Then we have 2 above and about 2.5 above. 2 plus 2.5 is about 4.5. We don't have to be perfect with this. You want to be close, though. Next one looks like we've got about 2 above and about 3 above, almost. It's going to be almost 5 above. What's that, about 1 3/4 above? 3 above. Add them up, it's about 4 3/4 above. This one's 1.5. This one's just over 3. It's going to give you about 4.6 or 7. Just over 1 above. Just over 3 above. It's going to be about 4.5 above. This is about 1/2 a block above. This is about 3.5 above. Add them up, it's going to give me about 4 above. Hard part's done. We don't have to add anything else. Where they're not overlapping, we just trace the wave that's there. There's nothing to interfere with this wave. There's nothing to interfere with this wave. The only point where we really have to add waves together is where the two waves overlap. Now, what are we going to do with these X's? Now comes the part in kindergarten grade 1 that everybody likes. It's those diagrams where you get to join the dots, see what picture it makes. That's what we're going to do right now, is join the dots and see what picture it makes. So we've got two waves as represented by those two black lines. But that's not what we see. At that moment, what we see is the red wave. What do we call that? Constructive or destructive interference? James, what is it? Good. It's constructive interference. Constructive interference occurs when you get two crests making a bigger crest, or two troughs, making a bigger trough. If you make a bigger wave, you're constructing a wave. You're constructive interference. Now, what I'd like you to do is take a look at the second one yourself. Keep in mind as you're looking at the second one that the first wave is above the horizontal axis. The second wave is below the horizontal axis. The overlapping occurs here. So that's where you really got to pay attention to it. Make sure that when you add those two together, first wave and the second wave, that the second wave are considered to be negative values. So for instance, the first one, we get 2 above and, 2 above and 2 below. What do those add up to give me? 2 and negative 2 adds up to give me 0. Okay, keep going on that and see what you end up with next couple minutes, okay? See what kind of interference we end up with and see what the pattern looks like. Okay, let's have a look as a group here now. Let's look at, we looked at line number 1 already. Let's look at line number 2 here. Line number 2 looks like we get 2 above and about 2.5 below. What's that give me? 2 plus negative 2.5? About negative 0.5, roughly. About 2 above, about 3 below, gives me about negative 1. 1.5 above, 3 and a bit below, gives me about negative 1.5. 1.5, 3.5 gives me about negative 2. 1 above, 3.5 below gives me about negative 2.5. This one's about 1/2 above, 3.5 below. Well, the rest of the lines are all easy, right? Because there's nothing to add up. Just trace the path that they follow. What's the resulting waveform look like here? Join the dots. This is the fun grade 1 part now. So you get 2 waves, but when they're passing by one another, it doesn't look like 2 waves. It looks like 1 wave. It looks like 1 wave that is bigger or smaller? Joe? Smaller. What do we call this? Destructive interference, yeah. Destructive interference. Now, it's not complete destructive interference because we're not completely canceling the wave out, but it's still destructive interference. Okay, let's shift gears a little bit before we come back to interference. Let's define a new term, diffraction. Diffraction is the spreading out of a wave. If you have, let's say, water waves approaching some kind of concrete barrier like this, these water waves approach this concrete barrier. They hit 2 openings in that concrete barrier. So part of the wave makes it through. Right? Part of the wave makes it through like this. But on the other side, it doesn't look like this. There's only a little bit of the 2 waves that make it through, but those 2 little bits spread out like this. That's called diffraction, the spreading out of a wave. Now, diffraction, the spreading out of a wave, is determined by a couple of different factors. First of all, the size of the opening. The smaller the opening, the more the diffraction. In other words, the smaller the opening, the more the wave spreads out. Okay? What about the frequency? This is always a hard one for me to remember. Through high school and even through university, I never remembered what effect frequency had on diffraction. Always remembered that it had an effect, but I never remembered which way it went. Was it high frequency, more diffraction, high frequency, less diffraction? And you know what? To this day, I still can't remember how frequency affects diffraction. I don't know why. Yeah, I can't remember it on its own. But early in my teaching career, I figured out a way to figure it out. Okay, this is what happened. When I was in my first year teaching 19 years ago now, I lived, I don't know if you guys know where this is or not. At the bottom of the hill, just below OJ, are these brown apartment buildings. You guys know what I'm talking about? Okay, just behind the courthouse. Okay, just behind the courthouse. So I lived in there. That's pretty much at that point where every brand new teacher lived, because that was the only apartments in town at that time. There were no condos, there were no apartments other than those. Okay, I used to, when I was single, I used to fall asleep listening to the radio, listening to talk radio. Okay, I always had to have a voice. Okay, so I'd turn on this radio show that I like to listen to on talk radio, and I'd fall asleep to that. I just set the sleep timer on my alarm clock. It would turn off in 59 minutes. I'd be sound asleep. It was all good. Then one night, I turn on my radio station, try to tune in the call-in show that I like to listen to on talk radio, and it wasn't there. It was something else on. I'm like, I can't listen to this. I can't fall asleep if I don't have my radio show. So for a few days, I can't fall asleep. Okay, I'm having a tough time falling asleep because I'm so used to listening to this talk radio show at 11 o'clock at night on my radio, falling asleep to that. Well, then one day I'm coming home from school late. Okay, at that time, the school was over where JP2 is now. Coming home from school really late. And I discover that, oh, wait, my radio show is on the radio. It's just on a different station. It switched stations. Perfect, right? So I go home. Driving home, I'm listening to my radio show. Okay, turn off the radio. Go into the apartment. Okay, get ready for bed. Go to bed. Turn on the radio to my new station. Can't hear it. Can't hear anything on this new station. When I listened to it at first, okay, before it went off the air, or before I thought it went off the air, I was listening to it on AM radio. I don't remember what the station was now, but it was AM radio. I could hear it in my apartment on AM radio. When I was listening to it, when I rediscovered it in my car over where JP2 is now, I was listening to it on FM radio. But when I got to my apartment, I couldn't hear the FM radio station in my apartment. Why? Well, this is what helps me remember how frequency affects the amount of diffraction. Here's my radio wave. The radio wave coming over the top of the hill. It wants to go straight like this. What does a radio wave do, though? Well, the same as any other wave. When it goes over a barrier or around a barrier, it spreads out. It spreads out like this. That's my AM radio station, my low frequency radio station. If you guys have ever looked at a radio dial, it'll say kilohertz for AM versus megahertz for FM. So my low frequency, I could hear it. Why? Because low frequency diffracts enough for me to hear it. But when I went to my high frequency, my FM radio station, waves that are really, really close together, high frequency, what happens to them? Well, they still diffract. But they don't diffract as much. I can hear AM in my apartment because AM, small frequencies, diffract more. I can't hear FM because high frequencies diffract less. Now, why when I was over here, way over here at the school, was I able to hear my FM radio station? Yeah, it had time and space to diffract more, right? To spread out more. It just doesn't do it as quickly as it does for AM radio waves, because FM radio waves are higher frequency. So what's our conclusion here? The frequency of the wave does affect how much waves diffract. Higher frequency waves, higher frequency, like for example, FM radio waves, we get less diffraction. So I don't have to memorize that. All I have to do is go back to 1995 or 1996 when I'm trying to listen to my when I'm trying to listen to my radio show at 11 o'clock at night, and I can't hear it on FM, but I can hear it on AM. All I have to do is go back to that, and from that figure out that FM radio waves don't diffract as much as AM radio waves. High frequencies diffract less than low frequency. What about wavelength? I never remember this one either. But this one's easy. As long as I can remember frequency, I got to remember that wavelength is opposite. So if you have a higher wavelength, what are you going to get for diffraction? Spread out waves diffract more. Exactly the opposite of frequency. Because if we look at the equation, V is equal to F times lambda, rearrange that, lambda is equal to V over F. As F goes up, lambda goes down. As F goes down, lambda goes up. Is that okay? Tomorrow we're going to tie the two things that we've just done together, interference and diffraction. Then we're going to look at how sometimes waves that diffract will also interfere and produce sometimes a kind of a crazy pattern of interference. That's it for today though, guys. We'll pack it up here now.